Okay, it's 2:02 p.m. We're going to go ahead and get started. Okay, and don't see anyone else waiting to join. All right, I'm going to go ahead and share my screen. All right, announcements. I sent out an email. You don't have to show up for lab tomorrow. It's recorded, it's online. It's on the topic of isomerism. And I will provide the links for that before tomorrow. Okay.
Dr. Trump, this may be a weird...
Okay, and I have Monday's lecture. I have that recorded, processed, and I have the link posted on Top Hat.
Dr. Trump, I have a question. Do we have to like...
Okay, there won't be a separate Top Hat for lab. That's going to be in with your lecture. So you can find the links later today for the lab videos on Top Hat. And I've made a folder called lecture videos.
Okay. Dr. Trump, someone was trying to ask a question. I don't think you were able to hear them.
Okay.
Oh, that was me. I just wanted to ask, do we have a lab notebook part of this upcoming lab? And if we do, how do we just submit it to the grader?
No, there won't be a lab report as such, but there'll be some online questions that you answer online. But there's no lab report that you'll write in your notebook for tomorrow's lab. Okay?
So our lab from last week, we didn't never get to finish that, right?
Right. So it'll be next week before you get a weight. So that's
Okay.
actually due a week from Friday. Okay, I'm going to go through this, through the review fairly quickly here. In most of the course, we're going to be talking about mechanisms and how they occur. And these will help you understand why we get a certain product and not another product. We'll use arrow pushing very extensively. Oftentimes, thermodynamics and kinetics will help us to decide whether a mechanism is reasonable or not. Okay, we looked at the chlorination of methane. This is the overall reaction. or methane and chlorine react to form chloromethane and HCl. This is pretty atypical of most of the reactions that we're looking at because it does involve a free radical. Okay, remember, a free radical is a species that has one or more unpaired electrons. And a free radical often undergoes a chain reaction. Okay, the key word here is propagation. Okay, once we initiate the free radicals, once we produce the free radicals, they react and generate new free radicals, which then continue to react until termination reactions occur. Right, so this is the arrow pushing mechanism for initiation. And we use a single barb fishhook arrow to show the movement of a single electron. So this is homolytic bond cleavage. Okay, one electron goes to this chlorine, one goes to the other. Almost all of the other mechanisms that we'll look at will involve heterolytic bond cleavage. And in heterolytic bond cleavage, find the camera here. Okay, I want to make sure, there we go. Okay, I want to make sure I'm on screen. In heterolytic bond cleavage, okay, such as this, both electrons go one way or the other. They'll move toward the more electronegative element. And notice we've got the double barbed arrow here. Okay, so both of these have no charge. A will become positive, B would become negative. In contrast, if we're moving a single electron, okay, then we use the fishhook type arrow. Okay, so these chlorine atoms are now free radicals. So that is the initiation step. This does require ultraviolet or blue light. Okay, it won't happen in the dark. Okay, then you have propagation steps that can take place. And propagation steps will generate new free radicals, as the name implies. Okay, so what happens here is this CH bond splits homolytically. One electron gets paired up with the chlorine, we form HCl. One electron is left behind on the carbon. Okay, this is another propagation step. Okay, that methyl radical can combine with a chlorine molecule which was not photolyzed. It splits up the electron pair in the bond. One electron forms this bond with the carbon. the other one is left behind on the other chlorine. Okay, some of the termination steps. Okay, termination steps occur when two free radicals come together to form a bond. This is one. These are some others. Okay, two chlorine atoms can come back together to form a chlorine molecule. Two methyl radicals can combine, and then we can have collisions with the wall.
Dr. Trump, I was confused on what exactly the definition of lytic is, like homolytic or heterolytic.
Okay, back here, okay, homolytic means the bond splits symmetrically. Okay, this is homolytic. Okay, we have a pair of electrons in this bond. Okay, one electron goes this way, the other one goes this way, so it splits symmetrically. This is heterolytic. Okay, that means that both electrons go to one side or the other. Okay, so that's what the difference is. Equilibrium, this is a review of equilibrium constants. This will address this oftentimes. Okay, we'll talk about how sometimes we need to supply an excess of one of the reactants if the equilibrium constant is not favorable, okay, in order to shift it toward products. Or if we remove a product, that will shift it toward products. Okay, delta G is an indication of spontaneity. If delta G has a negative sign, it's a spontaneous process. And if it is spontaneous, the equilibrium constant will have a large value. Delta G depends on both enthalpy, or the heat exchange that takes place, and entropy, which is an indication of molecular randomness. So you have to consider both of those, entropy and enthalpy. All right, if you have a large negative delta G, then the reaction equilibrium constant is very large, and you have almost complete conversion to products. Okay, we saw with the chlorination of methane, I believe the delta G is something like negative 108. This graph only goes up to negative 20, so essentially 100% of the reactants go to products. Okay, again, review of the sign. Negative delta H is exothermic, positive delta H is endothermic. Okay, some of the things that contribute to entropy: increasing the heat, increasing the volume, the number of particles, changing the phase, for example. If we go from a solid to a liquid, the liquid is more disordered. The gas is more disordered than a liquid. If you have more moles of gas on the product side, that's higher entropy. And also, if we have a molecule that is an open chain, but it forms a ring, okay, the ring has less freedom of movement, so there's lower entropy. Okay, we can estimate delta H using bond dissociation energies. and that's what we did last time. Okay, so when a bond is formed, okay, the sign of delta H is negative. Okay, forming a bond releases energy. Breaking a bond absorbs energy. Okay, if bond formation were not energetically favorable, bonds probably wouldn't form. Okay, so we can estimate, particularly in this case, because everything is in the gas phase, we don't have to consider solvent or anything like that. Okay, so we can consider the bonds that are broken, the bonds that are formed. Bonds that are broken, these have a positive delta H. Those that are broken, those that are formed have a negative. And overall, this is exothermic by 103 kJs per mole. The chapter after next, kinetics, will play a large part in determining the mechanism. But once again, rate laws are determined experimentally. Okay, this is a general rate law. The exponents don't necessarily correspond to the stoichiometric coefficients. The rate constant K is determined experimentally. These exponents represent the order. One of the ways we can determine order is what we call the method of initial rates. And what we do there, for example, is if we have two reactants, we keep one concentration constant and maybe we double the other one. And we see what that does to the rate. If there's no change in rate, if we keep A constant, we double B and there's no change in rate, that tells us it's zero order with respect to B. If we double the concentration of B and it doubles the rate, okay, then the exponent is 1, first order. If it's second order and we double the concentration, that would quadruple the rate. Okay, this will be an important part in when we talk about reactions of alkyl halides. Okay, again, a review of activation energy, the Arrhenius equation. Okay, the different parts of the energy diagram. Okay, we have the energy of the reactants. There's an activation energy, okay, which is abbreviated as EA. Okay, that's the minimum energy with which the reactants need to collide in order to react. At the top of this curve is the transition state. The transition state is typically very short-lived. It's very difficult to observe. It may exist on the order of 10 to the minus 15 seconds or something like that. And then we have the energy of the products. Okay, so this is an exothermic reaction because the products are lower in energy than the reactants. Okay, here's a two-step reaction. This time we have an intermediate. Okay, the transition states are maxima on the curve. The intermediate is a local minimum. Intermediates may be short-lived, not nearly as so as transition states, and many times intermediates can actually be isolated or observed. Okay, so this is a two-step reaction. In this example, the first step is endothermic, and that activation energy is higher than in the second step. So this will be the rate limiting or rate determining step. It's the one with the higher activation energy, the slowest step. Okay, and then the second step is exothermic. This is exothermic overall. The overall change is negative 105 kJs per mole. Okay, I'm going to go ahead and go over this again. Okay, in the halogen substitution of alkanes, bromine and chlorine are the only ones that have any practical use. Fluorine is way too fast. It's uncontrollable. It's very exothermic. It reacts explosively. Iodine is way too slow. Okay, this is an important point. Primary, secondary, and tertiary hydrogens, make sure that you recognize the difference. Okay, with propane, the favored product is actually the 2-chloropropane. Okay, we get about 60% yield of that. And the secondary hydrogens are 4.5 times more reactive than the primary toward chlorination. Tertiary hydrogens, of which there are none in propane, are about 5.5 times more reactive than primary for chlorination. Okay, there's a couple of reasons that we get more of the more substituted product. The tertiary is favored over the secondary, which is favored over the primary. Okay, one reason is bond association energies. Okay, if we compare these bond association energies, the primary CH bond is harder to break than a secondary CH bond. Okay, a tertiary CH bond is easier to break than a secondary. Okay, and you can see that by these values of the bond association energy. Okay, that's one reason. Okay, tertiary is easiest to break. The second reason is the tertiary free radical that's formed is most stable. Okay, so the more substituted the free radical is, the more stable it is. Okay, and by substitution, I mean replacing these hydrogens with some R group. Okay, again, an R group is some general alkyl group. It could be butyl, it could be propyl, it could be any carbon chain. Okay, so the more substituted free radical is more stable. A methyl radical is the least stable free radical. Okay, so this is a comparison of this propagation step in the chlorination of propane. Okay, in green, we have the secondary free radical being formed. Okay, it's 10 kilojoules more stable than the primary. Not only that, it has a slightly lower activation energy, so it's formed faster. Difference of about 4 kilojoules. Okay, with bromine, okay, there is much greater selectivity. Okay, with chlorination, okay, the difference in activation energies was about 4 kilojoules. For bromination, between primary and secondary, it's about 9 kilojoules. Okay, we're getting the same free radicals, so it's still a 10 kilojoule difference. Okay, what is another difference between this diagram and the one you just saw for chlorine? What's another difference? Okay, let me show you the chlorine one. Okay, there's chlorine. There's bromine. Chlorine is exothermic. This one is endothermic, right? Okay, and we can see that the activation energy for that step is larger. It's larger for both the primary and the secondary. So bromination is going to be slower. It's slower and it's more selective. Okay, so for bromination, not only do you need to provide ultraviolet light, but you also have to heat it, okay, because it is a slower reaction. All right, this we did not cover last time, so this is new. It's a Hammond postulate. Okay, the Hammond postulate says that related species that are similar in energy are similar in structure. Okay, so in other words, the structure of the transition state resembles the structure of whichever side is closest to it. Okay, so for an endothermic reaction, the transition state resembles the product. For an exothermic reaction, the transition state resembles the reactant. Okay, so let's go back to this diagram. Okay, so this is an endothermic reaction, and let's say we can take either one of these curves. So for example, this blue curve, okay, because on the product side, that primary free radical is closer in energy to the transition state than what's on the reactant side. That means the transition state is going to more closely resemble the product in terms of structure. Okay, so in this, this is a propagation step, and so you'll be forming an HBr bond, and you'll be breaking a CH bond. Okay, so in this case, if it's similar to the product side, okay, that means that CH bond is going to be almost broken. The HBr bond is going to be almost formed. If we go back to chlorine, okay, since that's exothermic, transition state is going to be similar to the reactant side. And so the HCl bond is just starting to form, the CH bond is just starting to break. Okay, so here's bromination and chlorination. For chlorination, the transition state is closer to the products. And for I'm sorry, it's closer to the reactants. For bromination, it's closer to the products. Okay, so this is a diagram of what the transition state might look like. Okay, the CH bond is almost broken, referring to the diagram on the left. The HBr bond is almost formed. Okay, in contrast to chlorination, the diagram on the right, CH bond is just starting to break. The HCl bond is just starting to form. Okay, since we've been talking about free radicals, this is a related topic. Radical inhibitors. Okay, these are often free radicals themselves that produce termination reactions, or in some cases, they'll form a free radical which does not propagate. One practical application of this that's important is food spoilage. Okay, because oxygen, as you may remember, molecular oxygen, is in fact a free radical. It has two unpaired electrons. And so molecular oxygen can contribute to food spoilage. Another reason that we might be interested in free radicals is skin cancer, for example. Ultraviolet light can initiate free radicals, which can then damage protein molecules. Okay, so some examples of inhibitors are the antioxidant vitamins, vitamin E and vitamin C. If you go to the grocery store and in the cooking oils, you know, like the olive oil and the safflower oil and all the different oils, if you read the ingredients, okay, it might have vitamin E or vitamin C added. If you have a lot of double bonds in your fat or oil, it's very subject to free radical damage. Yeah.
So if you're using like ones like vitamin E, sunscreen, or like the aloe after you got sunburned, would there reduce your chance of skin cancer or put on?
It's thought to, yeah. Okay, if you have especially a fat or oil, and you start to form a free radical, okay, by the action of molecular oxygen and light, that free radical then undergoes propagation steps, and as the diagram on the left shows, each one is exothermic, and so it just keeps going. But an inhibitor, okay, will produce a very stable free radical in which the next step is prohibitively too energetic. Actually, let me talk about a couple of other inhibitors that are sometimes added. I think I've got this right. Okay, this one is called BHT, and it stands for butylated hydroxytoluene. And sometimes this is added to baked goods. Okay, what happens is because of these bulky T-butyl groups, okay, you form a very stable free radical, but because of the bulkiness, that prevents this free radical from propagating. Okay, next we're going to introduce what are called reactive intermediates. Okay, we've already talked about free radicals. Reactive intermediates are short-lived species, but they can sometimes be observed. They're often not present in very high concentrations because they react as soon as they're formed. In fact, that's the definition of a reactive intermediate. It's formed in one step and then it's consumed in a subsequent step. Okay, so we'll consider carbocations. And carbocations will have a positive charge on the carbon. The hybridization of a carbocation is sp2, and so it has a trigonal planar geometry. So this is for the methyl cation. The methyl cation has an empty p orbital which is perpendicular to the molecule. Okay, carbocation stability is, the order of stability is the same as for free radicals. Okay, because free radicals and carbocations are both electron deficient species. And so the same factors that stabilize free radicals also stabilize carbocations. Okay, so again, more highly substituted, that is tertiary carbocations are more stable. Methyl carbocations are the least stable. So it's tertiary, secondary, primary, and then methyl. Okay, there are two reasons why additional substitution stabilizes a carbocation, and we can say the same thing about free radicals as well. Okay, the first is what's called the inductive effect. Okay, with these, this is a tertiary carbocation that's shown here on the left. Carbon is slightly more electronegative than hydrogen, so the carbons are pulling electrons away from the hydrogens. And so that means that these methyls are electron donating. They'll push electrons through the sigma bonds. Okay, and that's what's shown here. Okay, so that's donation of electrons through the sigma bonds. Okay, the other reason is something called hyperconjugation. Okay, so this is an example of a primary free radical. And with this methyl group, we have sp3 orbitals, which form sigma bonds to these three hydrogens over here. There is a weak, kind of like a pseudo-pi overlap, a weak overlap between the empty p orbital and this filled sp3. Okay, and that helps stabilize the carbocation. And if you have three alkyl groups, okay, they're going to stabilize it even more. Okay, another big factor that can stabilize carbocations and free radicals as well, but we didn't mention that, and that is resonance. Resonance is a highly stabilizing phenomenon. Okay, so here we've got a plus charge on this atom over here on the right, and we can move a pair of electrons from our double bond toward that, and we formed this bond. We used up a pair of electrons, so that leaves this carbon with an empty spot. Okay, so this goes back and forth, and because we can spread out that plus charge, that really helps to stabilize. Okay, this is the structure of a free radical. It is sp2 hybridized, like the carbocation, but instead of this orbital being empty, it has an odd electron occupying it. Okay, the same things that stabilize a carbocation will also stabilize a free radical. Okay, inductive effects, pushing through the sigma bonds, and hyperconjugation. Okay, same order of stability. And again, resonance can be very effective in stabilizing free radicals. Okay, resonance structures have to have the same number of odd electrons. Okay, and these structures that are shown here are. Okay, so what happens here is that we've got a pair of electrons in this pi bond. Okay, it splits up. One of them pairs with this odd electron, so we form a bond, and then there's an odd electron that's left behind. Okay, so this moves back and forth. The overall structure has partial double bond character on both sides of the central carbon. Okay, next we'll consider carbanions. Carbanions are the only reactive intermediate that we're going to discuss in this chapter in which carbon has a full octet. Okay, we're going to talk about one more after this one, but this is the only one that has a full octet. Okay, notice the resemblance between the methyl anion and the ammonia molecule. Okay, it's sp3 hybridized. It has a tetrahedral geometry. Okay, carbanions are nucleophilic and basic. Okay, nucleophilic, okay, that means they will donate that pair of electrons to something else that can accept an electron pair. They're basic, they'll donate that pair of electrons to a proton. Okay. Okay, it turns out that as far as what will stabilize a carbanion, okay, it's just the opposite of carbocation. Okay, so the less substituted carbanion will be more stable than the more substituted. Okay, because the carbanion now is electron rich. Okay, if we produce a carbanion, sorry, they tend to be extremely strong bases. Okay, so if we could produce a methyl anion, this carbanion, okay, it could remove a proton from ammonia. Ammonia is not very acidic. Its pKa is about 38. All right, the last of the four common reactive intermediates that we'll look at is the carbene. The carbene is unusual in that okay, it lacks an octet, but unlike a carbocation, it carries no charge. Okay, this is the structure of dibromo.
Okay, we don't have to do this. So, honestly, okay, when you look at you, earrings and makeup, hair, this, that,
Do you have
shoes.
a question?
Shoes, ladies, that, shirt, earrings, hair, makeup, kit. Okay, lips. I'll take this off.
Oh yeah, you're.
Okay, okay, carbene is sp2 hybridized. It has a vacant p orbital, which is perpendicular, a lot like a carbocation, except instead of a bond, it has a lone pair here in this sp2 orbital. Okay, so that means that a carbene can both accept an electron pair into the vacant p orbital, and it can donate a pair. Okay, so here's a summary of reactive intermediates. Carbocations are electrophilic, that is, they're electron deficient. They're strong Lewis acids, that means they're really good at accepting electron pairs. Even something that is not a strong electron pair donor. Radicals are electron deficient, and so for that reason, they have the same order of stability as carbocations. Carbanions have the opposite order of stability. Rather than electrophilic, they are nucleophilic. That is, they're very strong electron pair donors. That's what nucleophilic means. There are strong bases. Okay, so if you have a proton acid and a carbanion, okay, this can very easily pick up a proton. Okay, even as we saw in the example, even something as weakly acidic as ammonia. Carbenes are both nucleophilic and electrophilic. Yeah.
How are they neutral?
We can do the calculation here. Two H's here. Okay, so formal charge is group number, which is 4, or number of valence electrons, minus the number of non-bonding electrons, minus 2, minus the number of bonds, which is 2. So that gives us a formal charge of 0. Okay, and often the electron donation, electron acceptance occur at the same time. Okay, we'll talk about carbenes, particularly in reference to alkenes when we come to that chapter. Okay, and so that is it for today. Those of you on Zoom that joined late, I do have Monday's video posted, and there's a link to that on top half.